Welcome to this episode of Eureka. And in this episode, we are going to have a conversation with Dr. Arindam Ghosh. He is a professor of physics at Indian Institute of Science, Bengaluru. And he is a recipient of Shanti Sarup Bhatnagar Award in 2012 and the prestigious Infosys Award in 2020. Thank you for being with us on the show. It's a very wonderful opportunity for us to talk about some of the cutting edge work that you are doing. I went through your citations, both Shanti Sarup Bhatnagar Award and also the Infosys citation. I can see that the kind of area that you and your group is working are really frontline research, and many in India are not aware that there are labs in India, research groups in India, which are undertaking cutting edge research. So let me start with the first area that your group is working, which is on optoelectronics. And the citation in Infosys says that it's a interaction between light and matter. So if we recall our school physics, the interaction of light and matter that we see is like, for example, in some surfaces, light will get reflected. In some surfaces, the light will go through. This is what like opaque and transparent. That's what we usually understand, right? I mean, can you kind of explain when you say that the light matter interaction, what does it mean, so that we'll be able to understand the idea of optoelectronics much better?
Sure. Well, thank you, Dr. Venkateswaran. This is a great opportunity for me to be on your show and take our work to a broader audience. It's thank you for your initiative in this. And yeah, I would like to say what is the crux of our work, which is on optoelectronics. Optics is light, and electronics is flow of electrons. Right? That's how we make electronic devices. So optoelectronics is when these two processes are coupled, in which you either shine light to make electron flow, or use electronic flow to create light. Now, this is what our large field of work, all our cameras are essentially built on optoelectronic phenomena, in which when light comes, at some level, it gets converted to electricity. And that electricity goes and gets stored in the memory devices that are there in the camera. And you
so basically, like for example, the mobile camera, like digital camera, what we usually call, you say, is working on this principle.
So those are all built on
earlier time of film roll, where the light goes and converts a chemical change. That's a change, right?
Yeah, that is right. So that is also an optochemical change.
Yeah.
Here you take, and there are also some electronic movements are required. But I'm talking about now taking light and make electricity flow to give you performances, new devices.
Okay.
Yeah.
So you say this is here, for example, the light is shined to make the electrons move. When you say electronics, I mean, we are also thinking of electronic devices of various kinds, right? So can you extend to that? I mean, how does this optoelectronics look like? Only camera or other kinds of devices, other kinds of questions?
Yeah, I mean, camera is just one example. A lot of sensors are built on optoelectronic principles. The fundamental of it usually uses a semiconductor, although it is not always required, but many of times it's a semiconductor involved. When you shine light on it, the semiconductor absorbs that light, or the photons which come with the light, and that produces electrons in the semiconductor. And that electron is now ready to move around. So what you do is that you make this special semiconductor devices which are sensitive to light. Silicon is certainly one of the very important examples. So this is how the electronic industry gets connected to optical, different optical processes. And you get this kind of sensors, cameras, and many other devices also, which can be activated through light. So it's very close connection with semiconductor industry. Optoelectronics uses the semiconducting principles as well as device fabrication protocols to make optoelectronic devices.
Very, very interesting. So, for example, in lift, for example, modern day lift, If you are between the doors do not close down because there is a kind of optoelectronic device over there, right? In some malls, I mean, you have automatic door opening when you go near. There is a
Yes.
kind of optoelectronic device, right?
Absolutely. So there, of course, you'll see in various, even if you don't see, there are sensors.
Yeah.
So those sensors are either infrared sensors, and which you cannot visible light. You see only the visible light, right? Those which are in the range of 4,000 to 7,000 angstrom wavelength. But if you go to longer wavelength, lower energy, it becomes infrared. You can't see them, but they are also optoelectronic devices, because when those kind of rays fall on semiconductors, they produce electricity, and then that electricity activates some of the signals in the memory devices and processors. Some of the electronics devices which are connected to those infrared sensors, and that tells the door to open or move, or the lifts can move. All sorts of sensing technology depend very closely on the optoelectronic principles.
Very, very, very interesting. Let me move to another area which again your group works on, and one of the area which has brought you laurels, which if I read your citation, it says two-dimensional nanostructures, two-dimensional nanomaterials, and semiconductors. That's what it says. Let me, I mean, if again we recall our school mathematics, we have all read one dimension is like a line, two dimension is like a plane, and the three dimension is, of course, the world that we live in, or at least our everyday experience, right? I mean, X, Y, Z coordinates, and all this we have studied. And we are also told, for example, if you had a good mathematics teacher, that a plain paper is, we think it has two dimension, but it's actually not two dimension, because there is also some thickness for that paper. Although for practical purposes we may not consider it, but it's not really two-dimensional. So when you talk about two-dimensional structures, are you meaning like this, or is it really two-dimensional? So what does that two-dimensional nanomaterial mean?
Well, that's a very important and very interesting question, which is becoming important in the technological front now. You're absolutely right. When you take paper, typically a paper is 1/4 of a millimeter thick or around that. So it's still very thick thing. I mean, it's not, you can say it's still three-dimensional, but there's a very small thickness. So now everything in nature is three-dimensional. Everything has a thickness. Even an atom has a thickness, right? Or a size. So obviously, when you ask what do you qualify by 2D materials or 2D nanomaterials, it's essentially something which we now have a class of systems or materials which are just one atom thick.
Okay.
This has started about 15 years ago, approximately, when we started working on making devices from this class of materials.
Okay.
If the thickness of the material is reduced down to one atom or one molecule that the material is made of, it's really the smallest building block that you can imagine, isn't it? Right? For example, an atom will probably, and the size of a typical atom will probably be in the order of 50 to 100 picometer. Or if you take a lattice of a solid, it is approximately 300 to 400 picometer, which is about 0.3 to 0.4 nanometer.
Okay.
So you can see how thin that is. It's approximately, about 10,000 times smaller than the kind of paper thickness that you're talking about. Or if you take a hair, you cut it laterally by about 1,000 to 10,000 times, you go to that order of thicknesses. Okay. So that's when we are reaching the atomic or the molecular limit. So the kind of 2D materials or 2D nanomaterial that one is talking about today is a new class of materials where you can isolate individual atomic layers. So it's only one dimension is that kind of thick. The other dimensions are large, which is in the orders of micrometers to millimeters, centimeters long materials, but their thickness is of that one atom or one molecule.
So when you make such a two-dimensional nanomaterial, what is the new property that it acquires? I mean, what kind of curious things that happens over there?
Yeah. So that's very important, which is why many people are excited by them. There are what was very unexpected, that these materials actually contain properties which are completely different from their bulk counterparts.
Okay.
For example, one of the most important material in this class is graphene, which is one atomic layer of carbon atoms, which comes from graphite, which one layer of, you take one carbon layer of graphite, you get what is graphene.
Okay.
Now, the graphene is extremely conductive electrically. No one expected graphene to be so electrically conductive. Its electrons can move in graphene, tens to hundreds of thousand times faster than that they can move in silicon, which is why you can make electronics, extremely fast electronics, for example. Graphene, if you consider the thickness is just one atom, and you convert its mechanical strength to equivalent thickness of steel, it's about 200 times stronger than steel.
Okay.
Mechanical strength. You can stretch graphene by 50% of its size and release it, it will come back. So there are several extremely interesting properties, which is why people are trying to make flexible electronics with 2D materials, because they conduct electricity and you can bend them the way you want. You can have this property of light absorption, and which is what is the basic property that we are working on in many of the devices that we make. Not just graphene, but there are other semiconducting analog of graphene in this 2D material class, which can be used to make extremely high efficiency solar cells or optoelectronic devices, which includes solar cells and sensors, which can perform much better than the bulk counterparts like silicon and other things. So we are using these unique two-dimensional material properties to make devices, that can change our lives.
That's a very, very interesting. I mean, looks like science fiction. Kind of perhaps most likely the future world is going to be like that. I mean, that's what people would have felt in 1930s and 40s when the electronics was just emerging. We'll take a very short break here. It's a very interesting conversation. We'll take a very short break here and continue this conversation. Keep watching Eureka. Welcome back to Eureka. We are having a very wonderful, very enlightening conversation with Dr. Arindam Ghosh. He is a professor of physics at Indian Institute of Science, Bengaluru. Before the break, he was discussing with us the 2D nanomaterial, particularly graphene and other analogs with which you can create 2D materials, one atom thick. We will continue our conversation. So one question that comes to my mind is, what kind of devices are possible with such material which has very, very interesting properties?
Right. So there are many devices possible, and it is where people are looking very closely in the wide range of properties. And one of the most important properties is the semiconducting properties of these class of materials, and their usage not only as a semiconducting device, like the way we use it in computers, phones, where one is talking about field effect transistors, like you use a current and modulate it outside. Like digital electronics, you have got 0 and 1, right? That is how a semiconductor a transistor works, logic devices.
Yeah.
Now there are two-dimensional material-based devices which can perform this task at much, say, lower energy cost. Which is why people are very excited by that. For example, molybdenum disulfide is a material which has got superior properties compared to silicon, but since they're just about one molecule thick, you can circumvent several problems with the silicon electronics when they go down to very small sizes. For example, short channel, you can make extremely short channel, very high density integration, and so on and so forth. But more importantly, because they are semiconductors and they are completely on a surface, you can couple them to light. Optoelectronics and semiconductor industry could not come so close without the two-dimensional materials coming up. You can make memory devices. We are making, for example, in my group, one of the major thrust is to make neuromorphic devices, which means devices which can mimic the functioning of brain. That means making synapses, making neuronal protocols in which transfer of or the learning protocols using neurons. So you can make these very, very large class of functionalities and build devices with these two-dimensional materials, which are kind of uses their semiconducting properties.
Very, very, very interesting. One other area that your citation talks about is quantum technology. I mean, the word itself is like a very frontline terminology. So can you, very simple way, explain to us what is this quantum technology?
Right. So quantum technology is a very broad term. And today it's one of the most important future technology that the entire world is excited by.
Okay.
There are several aspects of quantum technology. For example, technology to make computers based on quantum mechanical principles, which we now call quantum computers, is a major part. But that's certainly not the only one. For example, making communication protocols which are secured from quantum physical principles and hence cannot be classically hacked by eavesdroppers. That's also another part of quantum technology. It's called quantum communications. But in addition to that, there is a whole new technology class which are built on quantum sensing and metrology. And those devices are expected to change our social life, our everyday life in a much bigger way, probably in the years to come. For example, if you would like to predict, detect earthquakes or submarines, or make extremely high sensitivity sensing of any form for metrological purposes, making standards. So these are important technological fronts that quantum technology is looking for. So these are the three main pillars of what is called quantum technology today.
So your group, what are you working on? I mean, this is a huge field, of course. Obviously, you won't be able to explore everything, but what is your group focusing on?
Right. So you see, our group focuses on one important component of quantum technology, which is required in many senses in quantum communication protocols, in quantum sensing, which is what is called a single photon detectors.
Okay.
And one of the important component of single photon detector is that we need to detect individual photons to know the information which is encoded in those photons. For example, it's the polarization of photons. It could be the phase. It could be the number of photons in a single pulse of light. So there are several aspects which require to be transmitted from one point in space to another, which are encoded in single photons. You see, if you in a standard sensing, which you mentioned in the beginning of this interview, that in the opening of lift and opening of various kinds of sensors, they are not really quantum sensors. There's a large beam of incoherent photons that are communicating, whereas that cannot work in quantum. So quantum, you need to go down to single photons and you need to detect single photons and their properties, their parameters and get the information to process it quantum mechanically. So our group has been working on creating single photon detectors as a 2D material based platform for making single photon detectors.
Okay, very, very, very interesting. I mean, so this essentially would mean that if you can use something like a light, I mean, of course, it may be infrared rays or visible light for transmitting information, like modulating it with, let's say, the number of photon or frequency, or as you said, number of photons in a pulse and so on and so forth. Then it would mean that huge quantity of data could be circulated, right? I mean, transmitted, which is today a huge challenge for communication. That's the breakthrough one can have if the quantum tech-based communication is possible. That's what I see. Am I correct in my estimation?
No, that's correct.
Yeah, that brings me to another part of your work, which is low temperature physics. So when we talk about physics, the first thing, of course, most of us would remember is Newton's law. I mean, in a sense that a very formalized physics, one can say, that emerged with Newton. So from that, if you look at the Newton's equation, I mean, I don't see anywhere temperature. So irrespective of the temperature of the object, the way the object will behave is defined by Newton's law. So where does the low temperature physics come? What does it mean?
So you see, the low temperature physics is does not conflict with Newton's laws in any manner, and low temperature is essentially a platform. It's a condition in which some of the fundamental properties of matter becomes apparent or detectable.
Okay.
And one of the most important beneficiary of low temperature physics is quantum technology itself, because many of the properties of matter, which are quantum in nature, becomes apparent or detectable at low temperature because they are usually of low energy. You see, if the physical processes that is happening in a material or in a system has very little energy, very small energy, then if you increase the temperature to room temperature, say for example, those properties get simply washed out. You cannot detect them. So one of the most important component of doing research on quantum area is to create an environment where such phenomena becomes immediately observable and you can manipulate them. For example, when people are making quantum computer today, they need to go down to temperatures which are millikelvin, which means in the order of 273 degrees below that of ice. Okay. And so that is seriously low temperature. So it's when you go to that kind of temperature, the entire system behaves quantum mechanically, and you can use that information, the quantum information, to manipulate to get devices which are completely non-classical. At high temperature, you get classical devices. At low temperature, you get non-classical information or quantum devices. So our work is very strongly coupled to low temperature devices because we work in the quantum area. We have these systems which can be cooled down into temperature scales of 270, nearly 273 below that of freezing ice, freezing water. And then we make devices to work at those temperatures and get the quantum mechanical properties out. That's the low temperature component.
Very, very interesting. I mean, one at the end of this conversation can see that how many of the areas that you are working on are interconnected, like how the 2D structure is interconnected with quantum computing, and that is interconnected with low temperature physics and so on and so forth. We have had a very, very wonderful conversation. For our lack of time, we may have to end this conversation now. But thanks for being with us in the show and explaining so beautifully some of the work that you and your group are doing. Keep watching Eureka. We'll come back with another interesting conversation next week, same time.